Geology is the study of the Earth. Geo meaning earth, ology meaning study of. Nowadays, it's not just the study of the Earth. That's kind of an old term it's just the study of the Earth. It's the study of the Earth and its systems. So you can't study geology without studying geography, mineralogy, climatology, the weather. It all affects each other. And it's taken scientists a long time to realize exactly how much it does. It all interplays with each other. So Alfred Wegener, back in 1912, he wrote a book called, The Origin of Continents and Oceans. He basically was ostracized for doing that. This book, because he proposed this new theory, the theory of plate tectonics. He called it continental drift. And he was, amongst other things, he was a meteorologist, a cartographer, a geographer, and a geologist, per se. They didn't really have that term geology back then, but he studied all these things. And this wasn't just something he came up with on a whim. He'd been studying this stuff for years, and he realized that if you take a map of the world and put it together, all the continents fit together like a big puzzle. And so, but he also studied stratigraphy, the different layers on different continents, and he realized they all match up. And then he realized the diamonds in Africa were the exact same kind of diamonds in Brazil. And he's like, so these were obviously put together one time. And he was laughed right out. I mean, everybody just made fun of him for this. He proposed this new theory. It was so radical that none of the other scientists, especially geophysicists, could wrap their heads around it. And the reason is because at this time, the Earth was thought to be just one solid rock, a very round rock. We didn't even know why planets were round, but we knew they were all round. And we didn't know why or how it could be, parts of it, the Earth could be moving around. Completely foreign concept to 99% of the scientists in the world. So in 1928, there was a conference of scientists held in New York City. It was the petroleum engineers, actually, hosted the conference, but it was all earth scientists that were there, and they were there simply to vote on whether or not to accept this new crazy theory. And because they could not figure out, the geophysicists of the time could not figure out how these planets could be moving. There was no energy that we knew of at the time that would make these continents drift around. So they decided it didn't exist. So they voted on it, and therefore it did not exist. A year after Wegener had died, another scientist, he put together that it made a lot of sense that this would work, and he wrote a paper on it and said that there's two energy sources that affect everything on the Earth. The sun, obviously, being one, and the other one was the heat of the interior of the Earth. We had volcanoes. We knew the inside of the Earth was hot, and he proposed that it was convection that was driving everything. And convection is when you have if you imagine a pot of water and you put a heat source underneath it, the water from the top circulates in series like this. And if you heat it up slowly, you can see that. If you take a pot, you get home, and I was going to do this and I just didn't get it set up. But if you take a pot and put some water in there and let it slowly heat up, and put a couple of drops of food coloring in there, you'll see that the cold water sinks and the hot water rises, and it'll do this. And he proposed that that's exactly what was happening, and that this was the mechanism that was driving tectonics, making all the continents drift around. So the sun is almost as important in plate tectonics as the interior of the Earth, the convection of the Earth. And that's because as we have the convection inside the Earth building up mountains and pushing continents around and causing everything, we have the sun, which is driving oceans and currents and stuff like that, and creating weather systems that's beating down the mountains. So the mountain building processes are called orogeny. That's not a bad word. It's a perfectly safe word to say if you say it right. That's the driving of mountain building processes. And so you have a number of different mountain building processes, but they're all called orogeny. So you have the mountains being built up, and you have weathering from the sun It evaporates water out of the oceans, and they turn into clouds and rain and snow, and it weathers everything and moves it downhill. And so that's called the hydraulic cycle, the water cycle. And so it's weathering all the mountains and everything down, while the interior eye of the Earth is building everything up. So the guy that proposed the convection was the mechanism. His name was Arthur Holmes. No relationship to Sherlock, at least not that I could find in my 3 minutes of research on that. Oh, one of the other major evidences that they found was that when basalt comes out of the ground, is an extrusive volcanic rock. So when it is forming, basalt is the thick black rock. Most of Hawaii is all basalt. We have lots of basalt here in Utah. When they would find these basalt deposits, basalt, one of the constituents that make up basalt is magnetite, and magnetite always points north. And so they would research these and find these little microcrystals of magnetite, and they didn't always point north. In fact, some of them pointed south, but a lot of them pointed all kinds of directions. And so when you take all those kinds of directions, put them all together, and put the continents back to place, they all point north or south. The north and south pole flip every once in a while. So, well, we had one land mass, Pangea. It was one land mass that sat on the side of the planet, and the rest of it was oceans. So if you take a ball that's lopsided and spin it, eventually, you'll notice there's a warble. No, it's a warble to it. If you do that on a ball of liquid, like we have in the interior of the Earth, then all those continents are going to break up and balance out. So that's what we have now. So, all right, magnetite. Lithosphere is the outermost layer of the Earth's crust. It includes the oceans. It's just the big thing. So if you imagine this crust, it's fractured. Think of a hard-boiled egg, and you've cracked the eggshell, and each of those little cracks, the pieces, are a continent that's drifting around on the hard-boiled egg. It's the same thing with the planet. You have this ball, and pieces are fractured, and they're moving around as continental or convection drives them. They move at different speeds. Some of them are moving at a rate of millimeters a decade. Some of them are moving 1/4 of an inch a decade. So they're not moving real fast, but they are moving. So obviously we don't feel them very often. I mean, we've had like 3 earthquakes in Salt Lake since I was a little kid. So
it's always the earthquakes that I'm trying to hook the induction with the earthquakes.
So you have this ball, you have these land masses. In order for them to move, you're going to feel an earthquake. Okay. So you have the Pacific Ocean on the side of the planet. It is a great big plate. That's the biggest plate. And as it moves, it's turning. And it's turning so that eventually Los Angeles will be in Burbank, California. So it's turning that direction. And as it does that, every time it moves, which is a few millimeters at a time, as long as it's moving real slow, we don't care. It's when it quits moving, then it's building up pressure, and then it releases, boom, you get a big jerk, and that's when it causes so much damage and destruction.
So the induction
is still driving that, yes.
Oh, okay, all right.
So if the heat comes up and cold magma sinks, and it does this, and as it's doing that, it's pushing things around on the surface. So earthquakes, you think of the epicenter of an earthquake, and that's where the actual fracture occurs. And there's 2 types of waves. There's primary and secondary waves. So there's P waves and S waves. And so the P waves are what travel out and go a long ways. And they can go a really long ways. S waves they're not as strong, or they don't go as far. But an earthquake like a magna, they most certainly registered it in Tokyo. I mean, they register every earthquake in Tokyo. So they have very sensitive machinery that detects it. And because of the way earthquakes travel through the earth, they can detect them. Sometimes they don't get them for a day or so, but they'll feel them. They'll be able to measure them. So, yeah. So I will diverge a little bit here on earthquakes. So I wasn't going to cover them a lot, but
that's fun stuff.
It is fun stuff. And so the type of fault we have here in the Wasatch Fault is not capable of producing what the news keeps telling you it's going to produce.
A big one.
A big one. The biggest one we're going to ever have here is going to be in the low 7s. This type of fault.
Still big.
It's big. Well, it's nothing like in California or Alaska where you get 9s and 10s.
Yeah.
I mean, that's total destruction. Here, we're not going to get that. 7, something like 30% of the buildings will receive damage, and something like only like 7 or 8 or 9% or like that will be destroyed. Okay, so water evaporates in the oceans. We have the hydraulic cycle, so you get it in the oceans. It goes up to the mountains. It rains and it washes stuff down, and so you have this hydraulic cycle. I mean, that's a very, very, very basic example of it, but that's how it works. Water is very erosional. You'll find mountains that sometimes are building, and they're building at the exact same rate of erosion of a river. And so you get these mountains that build up with a river channel right through the middle of them, and it just goes right through because they're going up slow enough that that river can just cut down through it like a saw. And so you get that. That's not very common. You can see that up at Martin's Cove, up in Wyoming. If you go up there, you can see where they have the highway goes around it, but there's a mountain there that's just literally sliced right down from the river, the Platte River, and it makes a perfect saw. So it's raising, but it's also cutting down through it. So the interior of the Earth acts plasticky, which is why it can convect, and so it's very much like plastic deformation. It's under a lot of pressure and a lot of stress and a lot of heat. So here's a cross section of the Earth's crust, and I will turn this around so everybody can see. You have the center is nickel and iron. So when we find a nickel and iron meteorite, we know it came from the center of a planet that exploded. That's how we know that. Then you have the inner and outer core. They are plasticky, melty rock. And then you have the mantle. The mantle is where we get magma from for volcanoes. And that's also where a lot of the minerals we like to collect come from. It's from the mantle. So if you like to collect peridot or diamonds, they form in the mantle. Diamonds form at 900 to 1200 kilometers down at a temperature of about 2000 degrees Celsius. So Celsius. Yeah, it's warm. 3,500 degrees.
It's warmer than St. George.
It is warmer than St. George.
A little bit.
Not much. So magnetite forms down there. Any of the minerals that are associated with diamonds all form in that one little zone. And so it's pretty far down there, and it's pretty hot, but things do crystallize down there because of the pressure. All right, so the Wasatch Fault, like I was saying, is what's called a transit or transitional fault or slip fault. It's 2 plates that are kind of sliding past each other. This one's a little odd because it's not only sliding, but it's stretching. And so when it does that, you get it. So the Wasatch Mountains here are a different plate than what we're sitting on. And if you go to the Wasatch Fault, you can actually put a light on each side. You can be on 2 different plates. So, and the plate that we're on goes from the Wasatch Fault to the San Andreas Fault. And basically think of a tennis ball that slammed into the wall, the other side of the fault, and then now it's bouncing back. And it's bouncing back at a different rate all the way across. So you get what's called Horst and Grabens, and that is mountains and valleys. So you have, if you've driven or flown over from Salt Lake to California anywhere, you'll see you have all these little mountain ranges with these big valleys in between. Those are stretch lines, and so as the plate stretches, you get valleys that fall and mountains that rise, and so that's what's causing that.
Huh.
So it's very unique around the world. In fact, as far as I know, that's the only. Well, no, that's the largest Horst and Graben deposit in the world.
Horst and Graben?
Horst, H-O-R-S-T,
Okay.
means mountain, and Grabens mean valleys, or vice versa.
Okay.
So this whole process of the mountain building and the weathering is all trying to reach what's called isostatic equilibrium, and that's where it's in balance. And so it's very hard to get there because everything's in flux, but it all wants to get there, get to that point of isostatic equilibrium. So if you drive through the Price area, you go south of Price, or even as you're coming into Price, you can see all those flat topped little mesas out there. Those are little mounds, mud mounds that were created when lakes were there, very deep lakes, and they were all chopped off. So you would think they'd all be flat, but they're not. Some of them are tilted up, most of them are tilted like various degrees of angles, and that's because the water that was chopping them off was very heavy. And so if you take them all and put them back down with the weight of the water that was there, then they're all flat. But now that the water's gone, they've all expanded and reached isostatic equilibrium. The next part of this is geologic history. We're going to take the entire Earth's history and put it in a month. I mean, in a year. So January through December. Okay. So the Earth formed about 4.6 billion years ago. And when I say formed, it's not like it just popped out and it was born. It started out as a ball of gas that condensed and condensed and condensed and condensed. And physicists don't know why, but when you have a ball of gas that starts to condense, it also starts to spin. And as it spins, it condenses more and it gathers up more stuff and brings it in. And now you have this snowball effect of a planet. And at some point, it became solid. So I don't know. I don't know how, why, or when. About 4.6 billion years ago, give or take a week. And Jupiter's in the process of doing that. Saturn's in the process of doing that. And then some of them, if they have a lot of hydrogen and helium, they burst into flames and we get stars or suns. So anyway, about 4.6 billion years ago, the Earth was born. In March, the oldest rocks on Earth surface are known from, and they're about 4.2 billion years old, and they're in Australia. In November, the end of November, go down at the end, primitive life forms started to form on Earth. And when I say primitive, I mean single-celled organisms. So very primitive. Then in December, the middle of December, dinosaurs appeared and disappeared. And then humans.
Like December 29th?
Yep. Or actually 31st.
31st.
Yeah.
The
Down here,
humans.
clear down here, humans came. Humans were basically the last 3 minutes of December. The Precambrian is when you have the single-celled organisms starting to come on, and then you have the Cambrian, they actually call it the explosion of life, or life explosion, during the Cambrian, which is 300 and something million years ago. And that's when we started getting multiple-celled organisms, and then eventually, here we are. So you can't really study all of geology without knowing a few things. Periodic table of the elements. I'll pass this around. There will be a test at the end. You should know everything on here. So we're gonna reference this a couple of times over the next couple of classes. I will have this chart here, so it's an open book test. So, all right. So some definitions I'm going to go over real quick. Mineralogy. It's the study of minerals. Seems pretty obvious, right? Petrology, the study of rocks. Sedimentology is the study of sedimentary rocks. Seems self-explanatory. Stratigraphy is the study of the strata in sedimentary rocks. I don't know why it has to be separate, but it is. Ig Met Pet was one of my favorite classes in college. That's igneous metamorphic petrology. And it's because when you're talking about rocks and minerals, the igneous and metamorphic rocks are lumped together because you can't talk about one without talking about the other.
Obviously.
And lithology is the study of rocks and hand samples. So you go out to an area, this is what geologists do. They go out to an area and they're like, ooh, I'm going to figure out what this is. And they gather up a whole bunch of samples and they take it back. That's lithology. Going back to the periodic table real quick. So we have elements, minerals and rocks. Everything is made up of molecules, which are made up of elements. And minerals are made up of molecules or elements. So you can have a pure element like a diamond, it's just pure carbon, or you can have a tourmaline that's made up of a whole bunch of different elements mixed together. And then rocks are made up of two or more minerals mixed together. So the definition of a mineral is an inorganic homogeneous solid with a defined chemical composition, a set crystal structure, and is naturally occurring. So it sounds way more complicated than it really is. So a mineral is an inorganic. It just means it's not organic. It didn't come from anything organic. An inorganic homogeneous means mixed well. You can't separate it without changing what it is. Like water is H2O. You can't take out an oxygen and still have water. You just have hydrogen. So it's homogeneous. You can add stuff like salt to it, and that makes it salt water, but you're not changing what water is, you're just making it salty. So a mineral is an inorganic homogeneous solid. Solid meaning it's not a liquid or a gas, pretty simple. with a defined chemical composition. Every mineral has its own composition, its own defined composition. Water is H2O.
So if water freezes, it's a mineral?
We'll get to that. So, quartz is always SiO2, pyrite is Fe2S3. You can't change that chemical composition without changing the mineral. For example, water is H2O. If you add another oxygen to it, you have H2O2. Anybody know what that is? Hydrogen peroxide. Yep, it's hydrogen peroxide. Not exactly life-sustaining if you drink it. Every mineral has its own chemical composition. A set crystal structure. There are 5 crystal classes. They are very defined. There are only 132 options for crystal shapes. That's all there is. And I know people have memorized those, but not me. So that's it. There's no other shapes that are available. That's all there is to it. So quartz has like 150 different shapes that it forms in. Calcite has over 200. Pyrite has about 200.
Shapes has got a subsection of shape.
Mm-hmm. Yep.
Okay.
Yep. There's
Now, when
lots
you
of
say shapes, you're talking about like
crystal habits.
the hedrons and all that
Mhm.
stuff?
Yeah.
Okay.
Polyhedron, hexahedron,
I like those.
dodecahedron. And the last part of the definition is naturally occurring. So when you say ice, are you talking about ice in your freezer or a snowflake?
No, because that would not be a mineral.
No, it would not, but a snowflake is.
Okay.
So there you go. So the definition of a rock is much simpler. It is 2 or more minerals mixed together or a non-crystalline mineral. So in a fossil, let's see, anybody want to venture a guess of the definition of a fossil? It can be a footprint that was never living, but it was made by something that was living. A burrow mark made by a worm. Again, the burrow mark is not alive, but we call them fossils because they're evidence of something that was once living.
So coprolite is a fossil.
Mm-hmm.
And
Absolutely.
illegal to collect.
That is now, yes.
It
Really?
is?
Yes.
Since when?
Coke-related?
Since
How
a
do
few
you
years ago.
know what
Since
it
new
is?
regulations.
Scratch and sniff.
No. No, that's not right.
When I was in college, I wrote a paper on coprolites for a term paper for a class, and I went and interviewed one of the anthropologists. They dig up human coprolites, especially the Native American ones, to study to see what they were eating and that kind of stuff. And the professor, I was like, well, I want to see one of these. He goes, you can't. They just stink so bad.
Really?
they stink just as bad now as they did then, maybe worse.
Really?
Because they're not fossilized.
They're not completely fossilized. They're only about 10 to 12,000 years old, and so even though they're dry and hard, they're not truly fossilized, and so they still stink. The next section is the rock cycle. I'm going to hold this up. Every rock you come across, not mineral, but rock, can be placed somewhere in the rock cycle. And it doesn't matter where you start in the rock cycle, you can trace where that rock has been and where it's going. And it's very important for geologists so they can trace a rock and tell you what you have and where it's been. So, for example, let's see, granite here. Granite is an intrusive igneous rock, and we'll get to that in a minute. And as it cools, it develops these crystals in it. So we know that it came from the earth, from the interior of the earth. Now, when it weathers, it can break down and turn into a number of different things. If you go up to the granite beds up in the canyons here, you'll find white granite. If you go to the edge of the canyons and all along the Wasatch Front here, you'll find that there's clay deposits. We mine it for making cement. And then if you go out to the Great Salt Lake, you'll find sand. So that clay and that sand used to be granite. So now sandstone out here, you find sandstone. Sandstone is the quartz grains from a granite like this, can be a quartz grains from a granite like this, that have been compressed and they get buried deep enough that they turn into sandstone. They get buried even deeper, they turn into quartzite. So now you have an igneous rock that became a sedimentary rock that became a metamorphic rock. Now, if that metamorphic rock, the quartzite, gets buried deep enough into the ground and goes back into the mantle of the earth and melts, it can turn into granite again. So, whole rock cycle right there. So I'll pass that around. So anyway, any rock you find, you can put in the rock cycle and trace where it's going and where it's been. That's the important thing to know, and it's very, very important for geologists. So you can have rocks that are igneous that become metamorphic. So granite, igneous, if it gets compressed and heated, it can turn into schist or gneiss. Again, schist is not a bad word.
But nice shits.
But you can have a nice schist or a schisty nice. So, again, you can put them on the rock cycle. Limestone goes and comes, sedimentary rock that turns into metamorphic rock. It can become marble or it can become a phyllite. So a number of different things. So, all right. So now we're going to go into igneous rocks. Igneous is it's either Greek or Latin. I can't remember.
It's probably Latin.
Okay, Latin means fire formed. You can tell what kind of rocks those are right off the bat, right? If they're fire formed, they're coming from volcanoes and deep in the earth. So that would be all of your, and they're divided into two groups. You have your intrusive and extrusive. Intrusive means that they cooled off on the inside of the earth, like granite, and extrusive means they cooled off on the outside of the earth.
So obsidian,
Mm-hmm.
is that considered igneous?
Yes.
Okay.
And that is extrusive. It had a super rapid cooling process, so that's why it's glassy. So rhyolite and obsidian are the same thing,
Okay.
but rhyolite cooled much slower. So if you've been out to Topaz Mountain and you've seen the whole mountain of rhyolite there, that's because you would think it was a volcano, but it's not really a volcano because it didn't erupt and explode and go into the atmosphere and all that kind of stuff. It's basically just a little crack in the ground that this stuff bubbled up and oozed out. It's like pouring a soda in a glass. You get the carbonation just goes everywhere. That's exactly what happened. So that's why it's all full of holes and bubbles. And if you go out there and look at it, especially if you go to where we did for the Red Burl, you can see where the lava, the rhyolite flowed, and the gas bubbles came out. There's huge sheets that are just full of bubbles. It's really cool. And that's where the mineralization also happens, is inside those bubbles. They're called lithofacies. And you get topaz and garnets and red beryl and amethyst and hematite and pseudobrookite and bixbyite all form in those. But it wasn't trapped in there. The gases that formed all those weren't trapped in there. They came in afterwards through steam that came up through the ground. And it would get trapped inside those bubbles and deposit the crystals. So intrusive would be your granite and your granite pegmatites, and those are fun. Granite pegmatites. We all like granite pegmatites because that's where you get
Smoky
quartz, aquamarine, topaz. Many gemstones come from pegmatites, and we like pegmatites. We do pegmatites. Utah is not known for its pegmatites. You go to Montana, Nevada, California, Maine, Colorado, yeah, you've got pegmatites galore. Now there is pegmatites in the Middle Mountains, and we get a lot of smoky quartz out of those. If you talk to some of the old timers from down there, they have smoky quartzes that are over 3 feet long. They're
Wow.
they're narrow. They're only 6 or 7 inches in diameter, but they're 3 feet long. I keep trying to find one.
It's just stories.
It could be story. I've seen them 2 feet
They
long.
grow every time they tell it.
Right, and they're probably 3.5 feet now. I'm going to pass around some of these. I'm going to pass around these two to begin with. These already came up. This is a piece of snowflake obsidian. This is rainbow obsidian. If you turn it in the light,
Your rainbows.
if you turn it around,
If you have a
with
single
good
source
light,
of light.
yeah, it's got good rainbows in it. This stuff is from Mexico. This is from Utah. We just gathered this up last week. So maybe use your flashlight on your phone to look at the rainbow one. So, obsidian.
You went out to obsidian beds and you used them?
I was there for all of like 2 minutes. I took a picture and left. Gathered up one rock.
Oh, is that
It's a little rainbowy.
Get it?
You looked at stuff.
So obsidian can be polished in a tumbler. Seth has got the system down now, so
Not
ask him.
easy.
No, it's not easy. In
Right
fact, I
there.
always make my
Fluoride.
kids start polishing obsidian when I was teaching them how to polish because it is the hardest thing there is to polish. Tumbling, cabbing, it is the hardest thing there is to polish. So I always made them start with it, and it's because it's so soft. So, the snowflakes in there are quartzes, little quartz blebs in there that form these little snowflake-shaped blebs. So the rainbow obsidian is got millions and millions and millions of microscopic little oval-shaped, rice-shaped air bubbles in there. And the air bubbles, some of the air bubbles have some girthite in them, and so they form rainbows when you put the light on them. So, a little stretch. The little bubbles act as prisms. So this is a piece of rhyolite. Marita collected this last time we were out there a couple of weeks ago. Has little pockets of amethyst in there. So I'll pass that one around. This is the stuff we were breaking up looking for the topaz and the red beryl.
Now I have a
That's
question.
just Searle.
So I have a rhyolite sample at home. It's got 2 yellow hair-like.
Coming back to Mount St. Helens for a minute. When Mount St. Helens erupted, it created this huge ash that came down the side of the mountain. It's called a lahar, and this is a lahar right here. These are pieces of lahar. These are volcanic ash and gas that came down. Lahars can travel at 700 miles an hour. So they are moving super fast, almost sonic speeds. And they come down and they bury everything in this hot gas, very sulfuric acid-ish gas. Pompeii was buried by a lahar. There's a number of lahar deposits in Utah. Any place where there's volcanic activity, you'll find lahars. They don't always travel at those speeds, and they're not always that destructive, but they tend to be.
So that's different from the pyroclastic?
The pyroclastic flows are different, yes.
Because it goes up, cools down,
And
and
then
drops.
Then drops. These come out the side of the volcano and just follow the ground whoosh,
Okay.
straight down. So these are 2 from here in Utah. They're actually from the same lahar flow down by Panguitch. Pass those around.
What are they
So
called again?
a lahar, Lahar.
What is this then?
That's rhyolite.
I would never have known.
So going back to the rhyolite,
Maybe like
when Mount
rocks.
St. Helens erupted, when they went in afterward, after it was done erupting, they found that in some of the ash it had little green blebs, and that wound up being basically obsidian. And so, but they were all small, I mean, like pea size, maybe even lima bean size, but they were very small. But it was clearly caused by the ash, and so people went in, they'd mine the ash, and then they would melt it down and recrystallize it into what was known as now St. Helenite or Helenite. And so these are some little examples of marbles that they have made from it. These are not natural; these are man-made, and but it's kind of cool because if you melt down the Mount St. Helens ash, it has enough lithium in it to turn the glass green.
It's actually faceted too.
Oh yeah, they got. When I first had the rock shop, I went down to Tucson, and you could buy carvings and stuff. I bought spheres this big out of it for like $5. It was so cheap. It was so common. So now it's expensive.
Everybody jumped on it.
Yeah. All right, this is basalt. Big chunk of black basalt. So black basalt is going back to the obsidian. One other thing about the obsidian. Obsidian is not considered a solid. It is considered a gel because it's very glass. It's very much like glass, and so it's not a solid until it devitrifies. Once it devitrifies, meaning it gives off all of the volatile gases in it, then it's considered a solid, and it's ugly. So nobody cares.
So it's not a mineral.
It's not a mineral. It's a rock because it has no crystal structure. Salt is another extrusive igneous rock. It is what basically makes up Hawaii. So it's very common in Utah. I'm sure I picked that one up here in Utah somewhere. Yeah, so down by Cedar City, west of Leeds, actually. If you just go out there to the river west of Leeds, it goes out there, and when you get out there, the road ends at the river, and there's a huge smelter there that used to process all the silver. And then you can look at the columns up there, and some of them are got to be 150 feet long and 6 or 8 inches in diameter. Anybody know the difference between lava and magma?
Lava's
Magma
above
comes from the
ground.
middle. Lava comes from the top.
Lava's above ground.
Magma is what you call it in the ground.
underground.
Hand it back to her. Magma is what you call it when it's still in the ground and liquid, and lava is on the surface. Around where we get volcanoes and thermal geologically active areas, we get geysers and mud pots and that kind of stuff. And so we get Yellowstone. Yellowstone has not always existed where it is today. It used to be on the Nevada-Idaho border, and it has moved to where it's at now. If you look at the geologic map, you'll see the perfect arc that it makes to get to where it's at. It's the same arc that if you look at Hawaii, it makes an arc, and that's because it's sitting over what's called a hot spot, and as that plate moves, it creates a new hot spot every time, and the hot spot's not moving, the crust is. So the volcano there, what's the big one?
Kilauea.
No, Mauna Loa.
Mauna Lisa.
Yeah. No, not Loa.
Mauna Loa.
Mauna Loa. Whatever it is. If you measure that from the base in the ocean to the top of the volcano, it's significantly larger than Mount Everest.
Tallest mountain. on
It
Earth.
is the tallest mountain on Earth. Yeah, it's significantly larger than Everest. It lacks the snow, and Everest lacks the ocean. So that's what happens when you get a hot spot. A hot spot's burning a hole, kind of like just a laser burning a hole through the crust and shooting up magma, and it does that. And as that plate moves, it creates a new volcano. And that's why they're in an arc. Same with the Aleutian Islands up in, in Alaska.
Alaska.
Yep. And same with Yellowstone. Like I said, it started in Nevada, Idaho, and moved up there. It didn't do it overnight. It took it a few minutes. So you also get we can use some of this for heat. We use a lot of it to make electricity. A lot of these geothermal active areas. We have a 33 kilowatt plant in Milford. If you saw the videos we posted, that's where the sulfur was coming from. The sulfur and the cinnabar was coming from there. The mud pots. They're like Yellowstone, not on steroids. What's the opposite of a steroid? Downers, yeah. You think of Old Faithful, and you think of the mud pots and the geysers up there, and the biggest geyser down here is like this big, and it spits up about this high. It's like, woohoo!
You tell those little bubbly ones.
Yeah, the little bubbly ones.
And then they go away.
They're cool.
Yeah, they're pretty cool. For Utah, it's really cool, you know. Anyway, we can use that steam, capture that steam because it's continuous. They pump it out of the ground, and if you go down there, you'll notice there's two pipes that parallel each other, and that's because one has got the hot steam going in it, and the other one's the return. So they take the water out and put it back in. If they take it just out, it creates earthquakes. If they put in too much, it creates earthquakes. So they have to keep it balanced. We're going to move on to sedimentary rocks. Sedimentary rocks are rocks that are caused by sediment. It's pretty simple. You get sediments. It can be delivered by rain, water, snow, anything that can cause it to settle. Wind is a big one. We can get a lot of wind, blows rocks from one place to another. There are two different types of sedimentary rocks, or weathering. I'm sorry, there's two different types of weathering: mechanical weathering and chemical weathering. Mechanical weathering is things like frost wedging. So when you're driving around and you see a mountain that has layers on it, and usually it's got vegetation growing on each of those layers. They're not very tall. They're like yay big apart. They look like game trails, but there's like hundreds of them on the same mountain. So that's frost heaving, frost wedging. That's when they get water in the ground there, and it freezes. And then as it freezes, it expands and pushes the rocks up. And so you get these rocks in these nice long little layers. I always call them frost wedges. Wind abrasion is another big one for that. You get wind, blows sand. That sand can carve other rock and blow it and carve it and cut it, and now it's depositing new stuff other places. In the Arctic, they find what's called ventifax. It'll be a rock that's landed there for some reason, and it's polished on one face. Often you'll find them polished on one face, and they wind up flipping over and getting polished on another face. And so you have these that have all these like really carved, polished, smooth faces on. They're really cool.
The natural sandblasting.
Natural sandblasting. That's exactly
So
what it
the
is.
swell, was that water or was that wind? By
So the
water
swell
or-
is it's completely
That's
different.
heavy.
So you have layers of rock, mostly sandstone there, and then underneath that great big oval is a huge salt dome that is moving its way up. And as it moves its way up, it's just pushing everything out of its way. And what we're seeing now is all those dog teeth on the east side, and they're not so prominent on the west side, but it's just coming right up out of the ground.
It's the swell, huh?
It's the swell. That's why it's called the swell. There is pressure releasing, so you can have a rock, and we see these all over out in nature. Is you'll have a big rock, and it can be sandstone, it can be limestone, it can be granite, and it'll be sticking up out of the ground. They're usually very rounded, and the outside layers are coming off in layers, like an onion. You can go up there and take off sections of them, just like an onion. And that's pressure releasing. As that rock has pressure being released off of it, layers pop off, and so you get these onion effects. Chemical weathering is things like rain. Rain lands on something, it slightly dissolves it and changes it and alters it. That is how Moki marbles are formed. So you have all the iron-laden sandstone of southern Utah. You get rainwater that comes down, dissolves some of that limestone or that ironstone. As the water goes through the rock, it picks up a little of the calcium out of the rock, and so it becomes slightly acidic. And then it hits that iron, and it dissolves the iron. When it gets so much iron filled in water, they can't hold all the iron anymore. It comes out in bubbles, and because it's underground, it's equal dimensional pressure inside, outside from all directions. You get bubbles. You can also get nice long pipes. They look like cast iron pipes laying on the ground. That's all chemical weathering.
So no heat.
No heat involved whatsoever. All right. Common sedimentary rocks in Utah include sandstone. I didn't bring in the sandstone. Oh yes, I did. So here's a sandstone. This is Dakota sandstone from down in Moab, from the blue crystalline actually. So it has azurite malachite on it. You can actually see where the water has deposited this ring in there of the malachite, the copper minerals. So the black in here is probably chalcocite. But that's sandstone. Sandstone we talked about earlier comes from the granite being weathered, and you get the sand out on the beach, and it gets buried, turns into sandstone, eventually turns into quartzite. Shale, another big common one here in Utah. Here is a piece of shale. It's got a huge trilobite that's broken in half right there. All right, so here is another limestone. It's got lots of the ammonites in it. This is from down by
Delta.
Yes. And the rounded blobs are called oncolites. And oncolites are fossilized algae, little algal balls.
And you just leave these out in your yard.
Well, I can't put everything in the house. I would try. Other common rocks, sedimentary rocks in Utah are conglomerate. Conglomerate is, you get conglomerates in deltaic plains, and so you have running water that washes out all the small stuff, leaves the big stuff, it gets re-cemented together, and you get conglomerate. Conglomerate is so common. And what's fun about conglomerate is that you can find all kinds of good fossils in conglomerate. Shark's teeth, dinosaur bone, wood.
Just from the float.
I was gonna say, I love that yellow cat. They've got the bone.
The problem with conglomerates is that
Oh, do you really?
it's like being in a big tumbler, and so you really get good preserved fossils in there. So,
Yeah, you can't get it out. You just
Yeah,
you
they're
see it
usually
in there.
well preserved in there. You can't get them out in case. Shale. Let's see. We just talked about shale. Siltstone. Siltstone's fun. We get a lot of siltstone here in Utah. Siltstone is just that. It's made of very, very fine grain, like sandstone, but it's very fine grain. You can use it for all kinds of fun things like sharpening knives and that kind of stuff. So fossils, almost all fossils are found in sedimentary rock. I always think it's funny when people say, oh, I have a piece of granite that has a fossil in it. No, you don't. That doesn't happen. So, the reason is that if you have any kind of organic material that winds up in magma, it doesn't get preserved. So I say this, and then a guy brought me some pictures of some fossils in basalt in Hawaii. They had basalt run over the top of a car, and so he's like saying that was evidence of something once living. I guess you're right. All right, the third type of rock that is known is the metamorphic rocks. The metamorphic, meta means change, morphic means form. Yeah, just sit on the floor. And so these are all the rocks that have been changed from one thing to another. So sandstone going to quartzite, that is a metamorphism. So quartzite is considered metamorphic rock, or sandstone sedimentary. Marble. This is what used to be limestone. A little bit of slight cooking, and one of my favorite terms in all of geology is metasomatic alteration.
Say it again.
You're so easily amused.
Metasomatic alteration is when you have a rock that is in the process of being altered through heat and pressure, but then there's a chemical change as well. So you not only get a physical, but you get a chemical change. So in this case, the chemical change, or the change goes from limestone to marble, and what happens is the limestone is recrystallized, and it turns into marble. So There's a little bit of chemical and physical change there. Wonderstone is a rock hounding term. It's not a scientific term.
Right.
So we have stuff in Utah that is wonderstone that is granite. We have it that's volcanic ash. We have it that's rhyolite. So
Just wonder what it
It's a
is.
little bit rougher than just sandstone.
well, yeah, I mean, you have sandstone that has. When we say wonderstone, we're usually talking about the banding in there, and those are called Lisagon bands. Lisagon was a French physicist back in the mid 1800s. Brilliant man. He actually used these bands in wonderstone found in France, and he found them in plants as well. And he used that to predict wireless communication in the future. Yes, he did.
Really?
Yep.
The stuff from Vernon, though, that's ash, right?
The stuff from Vernon is rhyolite, so it's not
Oh, okay.
really ash. The stuff from Salina Canyon is volcanic ash.
Oh, okay.
Now, back up to the, how do you predict future communications?
I don't
Were
know.
there
I'm not a
mushrooms
brilliant
Were
physicist.
there mushrooms growing on it, or?
I don't know, but he predicted that we would use wireless communications
Oh,
from
boy.
his studies of
The Lusigon
Lisagon
bands.
bands. The banding. I don't think he
Yeah.
called them Lisagon bands.
Hey, Wagner, listen to this.
Fossils. Oh no, we've moved on to metamorphic rocks. That's what we've done. So here's a piece of schist. This is a garnet schist. This is garnet schist. This is from up. And make sure you get that pronounced correctly.
Garnet?
Schist.
Oh.
This is a schisty schist. This comes from up where we go and collect the garnets up in Browns Canyon in Dutch John. So you can see it's made up of, a schist is a granite that's been compressed. It's been compressed to the point where all the mica came out in layers and all the quartz would come out in layers. This is just a layer of just the mica. This is a big garnet right there. You can't really tell, but it is what it is. So,
Everybody else finds the garnets.
that's a pretty good size garnet.
Schist.
No, I just,
It's also getting all over your rug.
I did find that big, huge rock like this big that had tourmaline all over the top of it.
Out
The
there?
garnet.
Yeah.
It wasn't tourmaline.
Remember that? It wasn't? Or was it?
No, it was starlight. So this is a skarn is when you get metasomatic alteration in certain types of garnets. And depending on what the new chemicals are that get brought in, you get a skarn. And I love skarns because skarns produce all of our garnets, or a lot of our garnets. They don't only form in skarns, they form other places too. But in skarns, we get big garnets. So this is a big garnet right here, you can see. We have not prepped this one out. This is one that Marita found. Actually, there's several big garnets here.
Of course you did.
Yep, right. Garnet skarns produce
That's nice.
great minerals like this, garnets that we just love.
This is from Gold Hill. You go to that
Yeah, this one's from Gold
section
Hill.
up in the
Serious?
where they have all
that
these
is
garnet
nice.
rocks.
Oh, that's cool.
This schist causes problems in geology when you are building buildings and dams. You can see it's made up of all those layers of those plates of mica. And so the St. Francis Dam was built, and the engineers focused entirely on the strength of the dam.
Okay.
Not what it was.
And the geologists told them you cannot build a dam on schist, and they did it anyway. They thought if we build a strong enough dam, then it'll be just fine. But they build it on schist like this, and you can see all those little plates. Well, on this schist, after the dam started to fill up, it didn't take too long, a few years or so. I think 2 years. Anyway, that rock started to slide and it failed, killed 400 people. Wow. So we are done. We'll call that good.
Nice.
Yay! Thanks, Rick.
Thank you. Thank you.